Hello, good morning, everyone. Welcome to the Earth Engine India Users Community webinar series. This is the second in the series that we as a community started a month ago. Earth Engine India Users Community is a bunch of users and users of Earth Engine, users of GIS data and stuff like that. People who work on India-based questions and research topics using geospatial data. We have a online Google web forum where we take forward many of the interactions that start here or start elsewhere, and that's a way to stay in touch. This webinar series is another way of keeping up interactions and collaborations, just to showcase some interesting work that people in the community have done, share some skills and expertise, and take some questions and answers. So, like I said, welcome again to this webinar, for which we have this time Craig D'Souza, MD Madhusudan, Guneet Mutreja, Ujjwal Gandhi, and Devja Shah. Thanks to everyone who've been able to join us. All of you in the audience, those of you who were here last time, welcome back again. And those of you who've joined us for the first time, good to see you. And I hope you guys will stick around and come back again and again. So we'll get started with a quick round of introductions. I'll start with myself. My name is Pradeep. I'm an ecologist. I'm based in Bangalore, and I work as a researcher on ecology and conservation science-based research projects. Craig?
Hi, I'm Craig. I'm based out of Pune. I've used Earth Engine since the last couple of years or so. And I mostly work on hydrology, water resources related problems in using Earth Engine. And yeah, looking forward to sharing and learning from everyone here in the community.
Hi, I'm Madhu. I'm an ecologist and I work at the Nature Conservation Foundation. And I'm mostly interested in things related to the environment and changes to the environment.
Hi, I'm Guneet. I'm based down in Delhi, working for TCS. Side by side, I'm pursuing my master's. I've been working with Google Earth Engine for past 2 years and found it very useful in performing some of my studies with Google Earth Engine.
Hi, everyone. Good morning and Happy New Year. My name is Ujjwal. I work at Google India at the Bangalore office, and I'm part of the Google Earth Engine team, and I do a lot of trainings and outreach to the Indian users of Earth Engine. So great to be here.
Hi, I'm Devja, and I also work out of the Bangalore office, and I work as a project coordinator, sort of helping put together India-specific initiatives. So yeah, happy to be here and to answer any questions that you have.
Thanks everyone. Just a quick roundup. Guneet is here today to give us a little glimpse into some of the work he's been doing, some of the work he has been involved with, which has used Earth Engine quite extensively. And he'll talk to us about the work he did, the datasets he used, and so on. Ujjwal and Devja are here to make some exciting announcements of some of the exciting things that are going on around the Earth Engine users community and the Earth Engine India Challenge and so on. And Madhu is here to teach us some about supervised classification. But before we get down to the main topics of the discussion today, Craig will give a brief introduction and overview of the events we are running. Craig?
Hello. Yeah. So just briefly, since Pradeep has already introduced the community, if you guys tend to have questions regarding what the Earth Engine India community is, feel free to post in the chat window. You guys have already probably seen the Earth Engine community.in website that we set up, and where we'll be posting about different events, different meetups, different sharing scripts, sharing things we're working on. So feel free to check out that website, check out the forum, and post things that you find interesting out there. What we're doing right now is a community on air webinar series. So this is something that we've decided would be a good thing to have once every month. So the first Saturday of every month at 11 a.m. is we're going to have a webinar each month, and we're looking forward to have different speakers on to talk a little bit about their research, talk a little bit about how they've been using Earth Engine and what they've been able to accomplish. And besides the speakers who will talk about their research, we're also looking to have teacher skill sessions. So essentially, within the webinar itself, about 10 to 15 minutes of another speaker talking about how to go about a particular skill in Earth Engine, a particular type of problem, which may run across different disciplines, which may not necessarily apply to any one particular discipline, but users across whether you're conservation or water resources or urban studies, these skills could apply to you across different sessions. So in today's session, we have both Guneet and Madhu who will be speaking. So we got a lot of requests from many of you during the last session about regarding supervised classification. So we decided we decided to have Madhu on for that, and he'll be talking a little bit about his problem, the problem that he solved using supervised classification. Guneet himself will be talking about using different hydrological data sets to solve the kinds of problems you would come across in water resources. So yeah, I'll also be posting out a link to a Google form. I'm doing that right now, and this is for people who would like to suggest topics, suggest speakers also for future sessions. So feel free to fill out that form. Tell us what you would like to hear about, what speaker session topics, or even skills that you would like to learn. And lastly, also, as Pradeep mentioned, this is a community-owned effort. So we definitely want more of you to participate and join in. So don't necessarily think of yourselves as us as organizers and you as participants. Think of it as if you want to get in here and volunteer and pitch in and say, okay, let's organize a session on this, or let's do this. Feel free to write to us, and we'll be glad to take these things forward. Yeah, I guess we can go ahead. Pradeep, over to you.
Thanks, Craig. Just to reiterate what Craig just said, this is a users community, and users doesn't mean a very narrow definition of meaning of users. It is anyone who's used or wants to use or could potentially use sometime in the future. Curious people. We would like to have any and all of you be part of us, so we can all learn from each other. There's definitely a lot out there that many of us don't know, and it would be good to learn from each other. Looking forward to seeing more of you. amongst us. Moving on, so we will get down to the meat of things today. So first up will be Guneet telling us about some of the work he's been doing with hydrological monitoring using hydrological datasets on Earth Engine. Guneet?
Yeah, thanks, Pradeep. So, hi, today I'll be talking about one of my master's research, which deals with hydrological study of Sangpo Brahmaputra River, which starts there from Tibet and comes down to Assam here in India. So let us first understand what is this river system. So before moving in forward, I'll show you how this Indo-Himalayan river system look alike. So we have these 6 river channels with us, wherein 2 of those move towards the left side, as you can see, which are Indus and Jhelum river channels, and 4 of the river systems move towards the right, wherein we are most interested in Yarlung, Sangpo, and Brahmaputra river channel, which itself is very important in the lives of the northeastern people of India and the Tibetans. So this is how the watershed areas in Sangpo river channel look alike. So there are total 17 river channels with us, 17 watershed areas with us. Here we are interested to see whether or not the Sangpo river in Tibet has any impact on the Brahmaputra in India. So with the advent of some projects taken out by Chinese, which is some SNWTP, which is South North River Transfer Project, wherein in order to overcome the instability of the water distribution in our neighboring country China, so they are planning to transfer some of the water towards the northern side, which is more water scarce here. So just to give you a brief or a fact, there 80% of the water that Chinese have is there in the southern part. So with the increase in the population, they are facing a lot of water scarcity problems. So in order to overcome, they are taking several projects. So out of those, we are just studying if or not this Sangpo River, they disperse the Sangpo River. So can we be having any problems like drought in the eastern part of the India? So this is just a chart wherein this is just the diagram of the river, the watershed areas for the whole river channel. So this is how it will go about it. So we have done our studies for precipitation, snowmelt, discharge, runoff, and water transitional states. These all are major 5 indications, from which we'll try to predict if there is any chance that we'll receive the drought or not. So all these data are taken out from Google Earth Engine, is readily available there on Google Earth Engine, and we have just used it and analyzed to answer the question that we are having today. So this is how it will look like. This is the study measures, wherein we have done studies with 8 levels. So these are rainfall, precipitation, snowmelt, evapotranspiration, discharge, surface temperature, runoff, and the water transitional states. So I'll just now present each of those one by one, so that it will be more easier to see which all watershed areas have the maximum among all these 8. So this is how the monthly average rainfall data look alike, wherein this data is taken from data.gov.in. This data says Arunachal Pradesh and Assam receives almost same same rainfall. So throughout the year, wherein the quarter from July to September has the maximum rainfall that they experience in millimeter. Now this is what we have taken out from the Google Earth Engine, the CHIRPS dataset, which tells us the precipitation, and this study is done across all the 17 watershed areas for 15 years. So this clearly tells us the areas lying in the Assam receives the most precipitation as compared to any other area than this Tibet. So then we have the snowmelt study, wherein this study is also done for all the water water channels, all the areas, and this also claims that these three watershed areas receives the most snowfall. And just to mention, these three areas are the ones which are in the Tibet, but just above the Arunachal Pradesh. They lie in China, but just above Arunachal Pradesh, they receives the maximum snow melt throughout the year. This is what it claims. So snowmelt study tells us that the area lying above the Arunachal Pradesh is experiencing a very heavy snow melt because of change in the temperature, and all that water that goes into the river Sangpo just comes in Arunachal Pradesh, and which is received at Tuting Station, which is the very first over there in Arunachal Pradesh. So as far as discharge is concerned, this study is carried out by GWSP. This is Global Water Surface Project. According to this study, they just traced whole river in some 33 tiles, wherein this river includes the part in Sangpo in Tibet, then Brahmaputra in India, and Meghna in Bangla Pradesh. So out of those, 15 to 25 tile number experience the heaviest discharge, water discharge, and the Tibetan receives the river Sangpo in Tibet receives the minimum of it. This is the runoff, wherein it shows that runoff also is maximum in these two particular watershed areas, which still lies in the areas which are above Arunachal Pradesh, just above Arunachal Pradesh in the other country. So all these studies, claims, or we are just trying to check which is the area which receives maximum out of all these things. Then we have done a study of transitional states, wherein this is just a data set available on Google Earth Engine, which is done from JRC. So this is also done for all the 17 watershed areas, and it says the areas which are over here have the maximum seasonal water, which lie in Assam, have the maximum seasonal water as compared to permanent one. So as far as we know, yes, we receive annual rainfall. It's been a long time that every year we receive heavy floods in Assam. That is because of the seasonal water, and that's it. That is what we are trying to predict or check or estimate from where this water is coming from. So that is our study linked to. This is the inference that we have made. Assam has the highest seasonal water contribution, which is around 65% among the three states, which are Assam, Arunachal Pradesh, and Tibet. The main cause of seasonal water is because of high snowmelt that is happening across Arunachal Pradesh and the above areas, the areas lying above it, and the precipitation in Assam and Arunachal Pradesh area. So just to give a concluding remarks, the main contributor of the river Brahmaputra is still, as far as the study is concerned, we found it Arunachal Pradesh. So there is no chance that if the river Sangpo is diverged to some other way in some desert of China, will not receive any kind of drought. That is a good news for us, for Indians. But it has a very good impact on the floods. So it has some impact which can only be measured if we'll get the ground segment data sets from the water hydrological sites there in Arunachal Pradesh and Assam. So this is it. So with this, this is the conclusion remarks, wherein I found out, yes, we do not have any such kind of fear of the drought that can happen. But so yeah, with this, I would like to show you the data sets that I have used, which are readily available on Google Earth Engine. For the rainfall, which is tropical rainfall measuring mission from a NASA. Then precipitation, we have snow melt. Precipitation, this is chirps, as I already told. Snow melt is GL dash, which is also a product of NASA. Evapotranspiration, again GL dash, also product of NASA. Discharge, it is Global Water System Project. It is a separate study carried out. Then we have surface temperature, it is Modi's Terra Land surface temperature. Then runoff, again GL dash, and the water transition states from the JRC dataset. Yeah, now I look forward for some collaborations in one of the work that I am working on, which is finding out the informal settlements across the India. Just to tell, the informal settlements are those which have very clumsy or a very high amount of people living in very small houses, or what we call it slums. So this is the diagram that I've prepared. This is the project flow, how it will go. This is my thoughts. I'm open for collaborations, your views, your suggestions, and any kind of improvements that I can do. We can talk offline about it if you are interested in it. This is for the Earth Indian community. So with this, I would like to thank you all for giving me time to listen on to my presentation and my work.
Thanks, Guneet. Thanks for that presentation. Lots of interesting data sets that were used, and pretty interesting investigations you've done. There was if you can, there's a quick question on your presentation by Shubham. Can we make all of these charts or analysis in Earth Engine itself? If yes, can you please share an example?
Yeah, just to answer the question of Shubham, we can prepare all these charts in Google Earth Engine, but these charts are not prepared in Google Earth Engine, as we have just taken out the data sets or the analysis that we have performed on the data available on Google Earth Engine, and these charts are made outside the Google Earth Engine platform. But Google Earth Engine has a very powerful charting algorithms wherein we can prepare very beautiful charts, and that yeah, the very beautiful charts we can prepare in Google Earth Engine too. Yes.
Yeah, okay, thanks. So if there are any shareable examples, we will share them later on. But even if there aren't any that Guneet has, there are plenty of resources available on the developers forum and the documentation online. We will post a link to that so you can look it up. Thanks, Guneet. Next up will be Ujwal giving us some updates on the contest that was recently announced and the next rounds coming up and so on. Ujwal?
Yeah. Hi. Thanks, Pradeep. So as some of you may know, we are currently running a contest for Earth Engine. It's called Google Earth Engine India Challenge, and it's open to all the students in India. We just ended our round one this week, and the idea was that we have round one, which has some quantitative questions that participants can answer, and those who answer them correctly will qualify for a more kind of interesting and open-ended round two. So the round two is currently open, and interestingly, the topic for round two question is supervised classification itself. So that ties nicely into what Madhusudan is going to cover today. And the training data and the problem that we're going to solve in the round two is also set by Madhu. So I think it'll be interesting to what Madhu can show and talk about the supervised classification. And though the round two is kind of open only to the people who qualified in round one, the problem statement, the scripts are all open and available in the website. And I can encourage anyone who's kind of interested in Earth Engine to have a look and try to work on the problem. It's kind of an interesting problem, and there hasn't been too much work done on kind of India-specific classification. And I'm really interested to see what our participants can come up with. I'll briefly just show you the contest website and the resources there. So this is the website. The round one were about 4 questions, and these are all quantitative questions, and they use different data sets. So if you missed out on participating there, it would be nice to again go through these problems and see if you can solve this. It uses some basic Earth Engine skills, and I was impressed that we received a lot of entries, and I was impressed that some of the solutions were actually very creative and more efficient than what we had come up with the solution. So really impressed with the quality of participants that participated in round one. And this is the round two, where the classification challenge is highlighted, and we can talk a little bit more at the end of what is expected out of this. But and again, to note that if you did not participate till then, you are not eligible for prizes. Even if you solve the round 2 challenge, very nicely. But as a self exercise, it will be a really interesting, and I would love to hear people's feedback on what can we do to make this kind of classification better. All right. So that's it, and I think it'll be interesting to see what Madhu can tell us about how classification works in Earth Engine. So if you need a refresher on classification, it will be a good segment to watch and then attempt to solve the challenge that we have in round 2.
Yeah, thanks, Ujjwal. So I'll now take over and try to give you a quick introduction to supervised land cover classification in Google Earth Engine. So let me turn on my presentation. Yeah, so let me start by saying what we will not cover today. We will focus on the fundamentals of doing supervised land cover classification in Google Earth Engine. But what we will not do is get into the different types of classification algorithms that are there or their characteristics. We will not look at sampling design and how to collect data, training data, to label data, and all of those kinds of aspects. We won't get into too much depth on that. And we also won't look into the ideas of uncertainty in both the inputs and the outputs that go into supervised land cover classification. So I will start with an example image of Bangalore city from the Copernicus Sentinel-2 satellite. We start by seeing just the data from one band, which is the blue band from this image. It's not easy to make sense of this image. Being entirely in grayscale, we have to rely to some extent on the intensity of gray and to some extent on the texture of the image to recognize features in it. Still, we are able to recognize and distinguish built-up areas, which are light, from the areas that possibly have vegetation or water, which appear dark. But then, in the next frame, as I add red and green bands and display a true color image with 3 bands, red, green, and blue, more features become discernible. And yet, it continues to be hard, for example, to differentiate vegetation from water, or for instance, roads from built-up areas. But then, once I replace the RGB bands with the red, near-infrared, and shortwave infrared bands, features that were previously ambiguous, like vegetation and lakes, or features that were previously indiscernible, like roads, now become clear and prominent. So there are many things going on here, but I want to focus on 2. First, when we look at each image as humans, we are always unconsciously trying to recognize patterns. We recognize patterns in hue, in the saturation, in brightness, texture, that we then associate with real world features like a lake, or a road. This is a perceptual rather than a computational task, and humans are generally very good at it. So this is the way humans process large amounts of data, by breaking them into meaningful categories, or in other words, via classification. Second, as we have seen with just the blue band, the task of perceiving these real world features is very hard with very little data, but it becomes easier when we add both variety and quantum of data, as we did when we added information from the green, blue, near infrared, and shortwave infrared bands. The task becomes more and more possible. But then this is not without limits. As the complexity of the tasks grow, when we add more and more input data to the classification tasks, or as our tasks become more detailed and nuanced with respect to their outputs, we quickly begin to hit limits of human ability. But computers, as we know, are very good at handling such large and complex computational tasks, but they need help from humans, it turns out, with perceptual tasks. So wouldn't it be great if we could train a computer with this perceptual task, which it could then scale as the volume and complexity of the inputs and outputs grows? This is basically the problem that supervised classification solves. It's one of the powerful and generic machine learning approaches used to teach computers how to accomplish perceptual tasks that involve large input data and involve and also have subtly differing outputs, such as in assigning pixels in an image to meaningful categories. So, how is this done? Before we move ahead, it's useful to quickly remind ourselves about some remote sensing fundamentals. Differing land cover categories like water, vegetation, or built-up areas all have very different spectral reflectance patterns. What do I mean by that? In other words, they absorb and reflect very different kinds of light in the visible and non-visible parts of the spectrum. We can use these differing combinations of reflectance values to create what are called spectral signatures for different land cover types. Think of a signature like the shape of a graph for each of the land cover classes. As we can see, the shape of the graph we have for water here is of this sort. And for vegetation, it has a pattern that's very different from, say, built up areas. And what I want to highlight is that if you just look at the blue, as we saw, it was not very easy for us to distinguish between vegetation and water using just the blue band, whereas we did see that the built up areas were very different. But then the moment we put in near infrared, the reflectance patterns of built-up areas and vegetation become more similar, but they become very different from the reflectance patterns of water. And on the other hand, if we add software, the shortwave infrared, we start to see that all of them, built-up areas, vegetation, and water, have very different reflectance patterns. Now, we can use all of this to try and help us. So now out of this, we are able to generate a signature for a built-up areas, vegetation, and water. And we can try and, if we get a pixel with an unknown kind of we can match it up to unknown signature. We can match it up to one of these and see which of these it's closest at fitting. So now how do we do this? First, what I will do is I will run through the various steps involved in supervised classification of land cover types in the presentation itself. And then we'll move to Earth Engine, where we will actually run each of these steps in a simple and then a more complex example each of supervised classification. What I want to start by saying is that the entire code that we are going to be working off is available on this at this link. So you can go back to this. This is a permanent link, and you'll be able to access the code as we have seen here. And so even the graph that was published earlier and so on, you'll see links to many of these that you can access as we go forward. So there are 6 steps that I have kind of summarized that are necessary for us to get moving with supervised classification. So first is to prepare relevant image data. So what we will first do is identify a sensor, a satellite image, a satellite sensor from which we will get images, and we will import that into a collection. And then we want to look at this image collection with reference to a certain point or region, which we will then select. And then once we have done that, we use appropriate spatial, temporal, and other kinds of filters, some of which Ujjwal spoke to you about last time, and they're available. If you're not sure what this is, you should go to the docs and see. These are really, really powerful tools that Earth Engine offers you to try and start with vast amounts of data and very quickly narrow down to the things that are of interest and relevance to you. So we use spatial, temporal, and metadata filters to obtain a subset of images that we then composite into a single image. So we will do that using a median composite here, and then we will display that image. And after that, we will get down to label data. I will show you very quickly how we can label data and put label data together in order to start our classification exercise. Alternatively, if you have collected data in the field, or if you're going to do this on your own using the image that you have just, the composite that you have just displayed, you are able to do that either importing an Earth Engine asset or from a shapefile, and there are ways in which you can do that, to which I have put a link as well. And then what we do is we take these labeled data points and then create a signature for each of the classes that it represents using the composite image. So as we saw with the graphs that I showed you about the built-up vegetation and water areas on your screens a moment ago, we will create signatures for the different land cover types. And using those signatures, we will try and create a classifier. A random forest classifier is what we will use. And we will try and create a classifier which we can then use on the image to classify pixels that are unknown, that have not been known, and to tell us which of the categories it belongs to. And the way the classifier works is quite simple. And you can actually replace the random forest classifier with, say, a CART, a classification or a regression tree classifier, or a support vector machine classifier. And that's quite simple to do in Earth Engine, and that's exceedingly powerful. And then we apply the classifier and generate a classified image. We will see how to do that. And then finally, this is of no value if we do not know how good we have been at classifying something that is actually a real world category. So we will try to find out how accurate we have been with our classifier. So these are the steps that we will be looking at when we get to our, okay. Example, I'd like to begin with this example. So as I said, the same steps that I mentioned to you, I have outlined here. So if we did, so what I'm going to do to begin with is to run just the first parts of our script, where we load images from the Copernicus, the Sentinel-2 satellite, and we pick an area which is from the Valparai Plateau in Tamil Nadu in southern India. You'll see in a moment why that's the place of interest we've chosen. And we will filter it based on location, based on dates, based on metadata, and then create a median composite and select just the bands that carry information on each of these pixels, rescale their values, and then create one composite that we will then display. So, and that's what we will be doing right now. And as you can see, so what the area that we are seeing right now is an area which has some vegetation. It looks like it's the backwaters of a dam, and there are some drawdown areas of bare earth and so on that we can see in this image. So now what I want to show you is that as I start opening up so we can add features, as I have already done here. What I have done is I have put a set of points to denote which is water and which is vegetation. Now I could start by trying to get signatures of water and vegetation from this. But since I also want to show you how you can actually add your own features, what I will do is also show you how to create a new feature collection. So let's say I wanted also to segregate not just vegetation and water, but bare earth around the dam. What I can do here is that I can click on a new layer, and I can go to this wheel here and choose feature collection, and I will call this bare soil. And what I will do is I will add a property to this feature collection called label, which is just an index number of the okay. So now I can go about adding points that represent areas that are bare soil, because that is the third kind of class that I want to be able to classify using this. So I have added, as you can see here, 10 points of each of these. And now what I will do is I can actually merge all of this data together as so I have training points from water, from vegetation, and from bare soil, and I can merge this so since after all of these have been merged, we can get the signatures of the land cover types that we have chosen here and train a classifier based on the property that we've called label, which has, so they have an index number of 0, 1, and 2, which is the label, and that's what one needs to use to train a classifier here. And after that, we can produce a classified image, which we can then display using certain colors on this palette, and we will see how we can do that. So now if we run this, we should be able to see one layer, which is the composite that is loaded. But in addition, as you can see, now from having started just with vegetation and water, we now have 3 classes of land cover that we have managed to classify, which is water, bare soil, and but how good has this been? So in order to do that, there are built-in tools that allow you to assess the accuracy of what you're trying to do. And there is something called a confusion matrix that tries to say how much of the label data you got right. But this is what we are getting here is just the training accuracy, which is a measure of how well the classifier classifies data that it has already seen. And this is not really very useful. But when you have a larger data set, as we will see in a moment, you can keep one fraction as training fraction and train a classifier, and then use an independent validation fraction to do a much more reliable test of the accuracy of your classifier in labeling data that it has not previously seen. So now we'll run this and try to see what the outputs are with. So it has, so all the training data points that we have used have been, when the classification happens in the classified image, they end up in the right categories. So we get a training accuracy of 1, which is 100%, which is not very useful or surprising at this stage. But now let's get to a real world example. And in the real world example, what I will do is point to certain key differences from the simple example that we began with. So we will begin, the points I want to mention are that we will be merging very different kinds of image data from different kinds of sensors, from bands within different bands within the same sensor. We will be seeing how to import a large labeled set of data from assets. We will also see how to create a training and validation fraction from the labeled data, and see how to do an accuracy assessment. So without further ado, let's go to this, which actually also happens to be a starting script, a starter script for you to undertake this times the Earth Engine challenge that Google has kindly put together. So we will not look at some of the early parts of this, which is meant for visualization. So I will focus on parts of that script that has already been shared with you on that call. And I want to call your attention to specific parts of this. So here what we have done is, right at the top, we have an import, which is from an Earth Engine asset that we have imported this table called VLP underscore table, which has our labeled data. So what we now do is we take this labeled data set, add a random column, which adds to every row a random number between 0 and 1. And so we use 75% of the data to train and another 25% of the data to validate what classification, the classifier we've got, and see how accurate it is. So the way we do this is that we pick rows that have a value less than 75, and then pick rows that have values of greater than 75, and then get a fraction for training and validation. So that's one part that I wanted to focus your attention on. The second thing I wanted to do is that you are not stuck with just having to take one set of images and create a median. Now, you could be, for instance, be adding NDVI or the NDWI if you're interested in water. And then you can add these as bands to your composite, improve your classifier. And that is largely the task we are hoping you'll be able to do this time with your own creativity and ingenuity. You can also add other kinds of sensors, like this is the ELOS elevation data set, from which you can bring the elevation data, and you can add all of these bands to your composite such that you have now a composite that contains not just the raw band data, but also the band arithmetic in terms of NDVI and so on, and also elevation data from ELOS and so on. So now with that composite, you're now doing a training, you're getting signatures from just the training fraction of your data set and training a classifier here. And based on that, you create a classified image. Now you go back to your validation fraction and get the signatures of data points in your validation fraction, and then create a confusion matrix where you see how well the labels that you actually had on your validation data points match up to the labels that they get once they are classified using your classifier. And this is a measure of the accuracy of your classification. And what we have managed to get so far is we have, I think, about 8 categories here. Yeah, we have 8 categories. They're not continuous numbers. And this tells you, the confusion matrix tells you how many of the how many of the points in each of these categories have been classified correctly, in which case most of the points would lie along the diagonal here. Off-diagonal elements generally signify how, I mean, the places where your classifier is not performing as accurately as it would. So where we are right now is that we have trained a classifier with a model that has an accuracy of 81.3%. And what we would like to do, and at this point I invite Ujjwal to add anything more he has to this, we would like you to improve the accuracy of this classifier so that you leverage on what we have tried to learn today about supervised classification and solve a real world problem in terms of improving the classification accuracy of a land cover for this area of Valparai in Tamil Nadu, which has a very interesting mix of landscape types that you will read about a little bit more in the example. So at this point, I hand over to Ujjwal for any comments and further
actions. Thanks, Madhu. Thanks for that excellent overview of supervised classification, starting from very basic fundamentals, which was very helpful. And that was also a good segue into the round 2 of the contests. We also have some questions we will take. And in the meantime, if Devja, you have any more details to put out there about the contest, you can.
I think Pradeep just dropped out. Sound dropped out. Anyway, I have a few comments about the supervised classification. I can talk a bit about that. So as you said, we got about 80% accuracy on the classification, which is pretty good. But you might be wondering, what are some of the strategies to improve the accuracy? And that really depends on the area of study that you are trying to classify, and also the classifier that you're using. So that's why we set the kind of round 2 problem of the challenge to be very open-ended, and you could go in either direction. One way is you could try different classifiers and try tuning different parameters. If you look at some of the classifiers, they have tens or more parameters that you can adjust, and the value that you set will affect how the data set is classified. And some of these values would require domain knowledge of the area as well as how the algorithm works. And that's again an open-ended research problem. So you could try different classifiers, try tuning them to what is the most appropriate value for the area and the training data that you have to classify that. The other direction you could go is try adding more data sets. So for example, if you know that certain classes, the value of certain classes would be distinguishable using some other data set. Say, if you say rainfall data might affect how have very distinct values in bare earth versus vegetation. Then you could try adding a band of rainfall data and see if it improves your classification. Again, this is very open-ended. You have to kind of be creative and really think about what additional data sets that are available in our training that you can add and improve your accuracy. And the idea is that you add some data set which will help you distinguish between two different classes. So if the data set is kind of equivalent, it's uniform across all the classes, then you won't actually see the improvement. So that's why it's kind of an interesting way. I expect some people to go in one direction, some people to go in another direction, and it'll be interesting to see what people come up with. And I'll be happy to present some of the alternate implementations and how we can do it once the challenge is done. Thanks, it'll be interesting times.
Great. Thanks, Ujjwal. You had something to add, Madhu?
No, I just wanted to say that in Ujjwal has given some pointers. I just wanted to add one more thing, which is that it doesn't have to be a completely different kind of a sensor. One can also look at for certain kinds of land cover types, there are temporal signatures, and there may be ways of actually trying to creatively bring in such a temporal element into your signature in order to accomplish what Ujjwal said of trying to maximize differences between the classes using the bands that you add into your composite. There are a couple of questions. I don't know if I'll be able to answer all of them. I invite any of you to join in. And there's a question from Shobita: for large data sets, is there a way around error matrix calculation which stops due to image being too large, even when export to drive feature gives computation large message? So I think this is one of the things that has repeatedly come up in the developers forum as well. I think the rule of thumb has been that you may run into memory problems if you're trying to do everything on the fly. But whereas if you're doing an export, this is something that will use resources over a longer period of time, but it will finish rather than giving you a timeout. And the second thing that has been suggested is that the way Earth Engine is built, it's more efficient at running, at querying your validation data of a classified image rather than trying to run the classifier on the validation data set itself. And that being said, I think every script is different, and it would be much easier to get a solution by posting a link to a specific data set to see exactly how to debug a particular. I don't know, Ujjwal, would you have anything more to add to in generic terms?
I agree with that. I just want to quickly show you the debugging guide that we have. So other users can also benefit when you run into such problems. So let me share my screen and show you this debugging guide. So it's on the user guide itself. If you search for debugging guide, you'll get this page. And it tells you like the common problems you run across. And say there is some errors that you might get, things like...
Ujjwal, could you increase the font size, please?
Is it better?
Yeah, that's good. Thanks.
There's a section on scaling errors. So things like computation timed out, user memory limit, internal server error. And there are strategies here that are discussed to avoid these errors. And then there are some best practices section here where it tells you how to best structure your script so that you can take advantage of the computation platform and not run into any of the errors. So I would suggest if you run into any of these issues, look at this page, try out some of the strategies and see if that works. This is based on a lot of our experience and working with the users. So I'm sure it would help you and to solve some of the problems. But if you can't, definitely post a link to a script in the user forum, and we and or one of the users would be able to help you out. Thank you.
Yeah, great. Thanks, thanks both of you. In relation to computation timeouts and all of that, there's a related question. Maybe if you guys have something more to add, you could do so. Question from Shubham also touches upon lazy evaluation. He wonders if there's any hidden algorithms like lazy evaluation going on in under the hood, because Landsat has 30-meter resolution. So if I mark points on a map area as a training set, how is it giving good results?
So I answered briefly. The way you would mark points, training data, if you're creating training data in Earth Engine, what you would do is you would use your image that you're trying to classify. So in this case, you would create your median Sentinel-2 image, load it on the map, and then whatever you can see, you mark your training data on those pixels. So if you see a water pixel, you would go and mark in there. What happens is if you mark it on using the base satellite image or a map that is displayed, it may not match exactly with the image that you have because of the resolution difference. So Earth Engine would use the exact coordinates, what you mark, and use whatever pixel that falls into in your image to pick those values. So you are better off just using the pixel. What you can do is sometimes if this image is too low resolution to see what it is, you can kind of look at the base image and find out the corresponding pixel in the lower resolution image and mark your training data. But ideally, you would use your image that you're trying to classify as the base for creating training data. And for kind of real research work, you would actually go to the field and collect the data using a GPS, and then you would upload that to Earth Engine. And that's why you can be sure that you are standing at this location, this is bare Earth at this time, and then you would use that code, the lat long, to pick the spectral signature from the image.
Yeah, great. Thanks. Thanks for that. I also wanted to add specifically, sometimes when you're working with rasters, when you run into computation timeouts, there's the optional parameter called tile scale, and that's expressly provided for users to get around computation timeouts when memory exceeding is a problem. So lazy evaluation, computation timeouts. So that debugging guide walks you through many of these workarounds to get around problems. You should check out the tile scale parameter as well.
Pradeep, can I add 1 point?
Sure. Craig, you had something?
Yeah. So to the challenge of figuring out your training data set. So one of the things that I've found in my experience was guessing the number of training points is generally a difficult exercise. So for a certain region that I was trying in Western Maharashtra, I was initially trying a random process of generating random points and then labeling all of those random points. But that, even with the best of methods, that tends to be a very manual and time-consuming process. So then, as opposed to that, you could go with a non-random process, which is essentially something like what Madhu demoed today, where you just keep dropping points on a map on the image that you're trying to classify, and generate as many points as you want. So that tends to be a faster process, but then you can't necessarily use that same training data a subsection of that training data to test it out. There is a FAO user accuracy training guide that I can share with you guys maybe after this session regarding something like that. being able to test, figure out whether your testing data set is indeed random for real user accuracy.
Okay, great. So, any more questions? So we will share more. All the responses to the questions will be included in the slides, and the slides are already public. If there are, so I guess, Guneet, if you have something to add to what you have already presented quickly in a few minutes, maybe we'll go over. We're already at noon, but we will take a couple of minutes more of your time in the audience, please. And Guneet has useful things to show. So, Guneet, could you take over?
Yeah, thanks, Pradeep. I would just like to show the GL. This is how it looks like. Google Earth Engine. This is GL 2.1. Likewise, we have 2.0 also. So this is the kind of engine that has, which is evaporation, evapotranspiration, pressure, heat flux. So these all are the bases and the very important key factors in the hydrological model. I would insist that all of you to just have a look at this GL dash. It seems it is from NASA, is it?
Yeah. Okay. Great. That's the wrap for today. I think lots of interesting stuff we went over today. Guneet with his interesting project on hydrology in the Northeast and big rivers that form the lifeline for lots of people and animals and forests and everything in that region. Madhu with a very nice, excellent overview of supervised classification and how you approach thinking about it and refining it and assess your classifier performance and so on. And hopefully that's given a good groundwork for all the participants of the Earth Engine Challenge for the round 2. And thanks to Ujwal and Devja to being around to give clarifications about the contest and lay out the terms and all of that. And Craig, as always, for just being there and pitching in and helping with question and answers. So thanks to all of you in the audience for having been around today and participating. We will see you again next time. Thanks.
Bye, everyone.